Okay, hi everybody. So let's prove the chain rule. Let's do this one. Let f of xy be a function defined on some open set in the plane, let's say, and c of t be a curve in the plane. A, what is the chain rule? Okay, so A. The chain rule is d dt of f of c of t is equal to the gradient of f evaluated at c of t, that's a vector, dot product c prime of t, that's a vector. Okay, so maybe I say the chain rule is. Okay, done. Part B. Prove the chain rule. Proof. By single variable calculus, so this right here, this is a function of one variable t. Even though f was a function of several variables, we plug in all the dimensions, the components of this curve, and we get just dependence on t. So by single variable calc, the left side of this equation, in other words, this thing, by single variable calc, the left side, by definition, is the limit as h goes to 0 of f of c of t plus h minus f of c of t divided by h. Okay. So what do we need to do? We need to show that the left-hand side is actually equal to this right-hand side. That's not obvious at all. That this limit, by this limit I mean like this equation, I'll call it star, that this limit is secretly equal to the gradient of f evaluated at the point c of t dot product c prime of t, the velocity vector. So period. That is not obvious. That is not obvious. Okay, so we need to prove it. Okay, now if we know we need to get the gradient involved, then what we should do here is recall linear approximation that says f at a point x plus some movement vector h minus f at x, so the change in f, is equal to the gradient at that point x dot product with your movement. And that would be great if it was just exactly equal, but it's not exactly equal. There's an error term that looks like this, some error. We have no idea what this is, but we do know that if you move very small amount, then this error should go to 0. So I'll say where g of h goes to 0 as capital H goes to 0. So if we take capital H, very small movement in space, and we take it smaller and smaller and smaller, then the error will go to 0. So now what we need to do is somehow, here's the gradient. This part here looks similar to the numerator there. So maybe we can change something and then divide by h down here, and maybe it'll just work out perfectly. And in fact, it will. But the key is this part has f of c of t plus h. This part has f of x plus capital H. So what do? Well, we let x equal c of t and capital H movement vector be equal to, let's see, c of t plus h minus c of t. Why? So that this x of c of t will cancel with the minus c of t, leaving c of t plus h, which is exactly what we have up there. So this is to match. Let x equals this, h equals this, to match star up here. And let's even give this a name, double star. Match star and double star. Okay, now rewrite double star. With these new substitutions, we get f of, well, now x plus h becomes c of t plus h. Check this. If you put this and this, that really works. Minus f of x, capital X is c of t. And that is exactly the numerator up there. So things are going quite well for us. Equals grad f at x, which is c of t. And now things are going very well because the chain rule says that this should be involved, and that's exactly what we get. Dot, and now what's h? Capital H has to be this thing. C of t plus h minus c of t. And that is a vector. And guess what? We'd love if it was the velocity vector. It's not quite the velocity vector, but once we divide by h, it's going to be the velocity vector. Well, and we take the limit. So this is going to absolutely work out. And now this error term, I'm not going to write out this h, it's going to be too long, so I'm just going to keep it as capital H instead of plugging in, just because then it's easier to write it. Rewrite double star gives this, period. Okay. Divide by little h. Divide by the number little h. Little h. And take the limit as little h goes to 0. Note that as little h goes to 0, so does capital H go to 0. Why? Look what happens up here. This is capital H. As little h goes to 0, capital H becomes c of t minus c of t, which is the 0 vector. And it's really important that I said that, because now when we take the limit as little h goes to 0, capital H will go to 0, and so this will disappear. This will become a 0. And what is the left-hand side? We divide by h and then take the limit. That is exactly d dt of f of c of t. That's exactly star from above. The right-hand side then, well, the gradient at c of t doesn't change as we take the limit. But we had to divide by little h. But you see that this dot product, when we divide by little h, we're just going to put it into this side of the product. And so this part becomes c prime of t, the velocity vector. Once I divide by h and let the limit, I get the velocity vector. And then we get plus 0 over here. And so we're done, as needed. End of proof. Okay, so you should try this yourself without looking. And it doesn't have to be exactly how I did it. If you can explain it better, then explain it that way. Whatever is better for you. Do it that way, but do it without looking, and then if you get stuck, you can come back to my video and see this.